In the previous slides, we have talked about the paging allocation mechanism, and the most important component of a paging mechanism is a page table. The efficiency of a page table affects the performance of a paging mechanism. Nowadays, the size of a page table can be very large because the size of a process and the size of data becomes larger and larger. It is very common to deal with gigabytes or even terabytes of data. Therefore, the whole page table cannot fit in registers. Then we need to store the page table in the main memory as well. It can be kept in main memory with two special registers, PTBR and PTLR, which are shorted for page table base register and page table length register. The idea is very similar to the process memory access with base and limit registers. So therefore, for each data or instruction access requires two memory accesses. First, the memory access, we need to get the logical to physical address mapping from a page table. The other memory access to get the data or instructions from the physical address on the main memory. Since each data or instruction access requires two memory access, the efficiency will be really low. So how can we address this problem? Actually, we can apply the same strategy as we did for other mechanisms. We can use a special hardware to solve this problem. Here we use a special fast lookup hardware cache called the translation look aside buffers, which is shorted as TLBs, to address this problem. Then let's see how to use a TLB to speed up the paging allocation mechanism. For TLB cache, there are numbers of entries on it. Each entry consists of a key, or sometimes we call it a tag, and a value pair. The key or tag is the page number. The value of the entry will store the corresponding frame. Unlike the searching on the page table, we need to look up each entry one by one to find the result. On the TLB cache, we can compare all keys with a given local address simultaneously for lookup. It is extremely fast and no performance penalty. And also for some TLBs, it will store address space identifiers, so which is shortened as ASIDs in each TLB entry to indicate whether the entry belongs to the looking process or not. For efficiency purpose, the typical size of a TLB is quite small, so usually is 64 to 1024 entries. So due to the limited entry numbers, it cannot hold all the entries for all the processes. Therefore, the TLB miss could be happened. On a TLB miss, the system needs to get the entry from the original page table and then cache the entry on the TLB for the faster access next time. Then let's see how can we speed up the paging allocation with a TLB hardware. When a process needs to access the data or instruction stored on the main memory, the CPU gives the logical address. Instead of looking up the page table directly, the page number will be sent to TLB first for comparison to see whether this entry is cached on the TLB or not. If yes, it can directly get the frame for this page number and combine with the page offset D to get the physical address and access the main memory to retrieve the data or instructions. On the other hand, if the TLB cache miss happened, the page number will be sent to the page table on the main memory to find the corresponding frame, then combined with a page offset D to do the same progress. Actually, some system calls or services are frequently requested by the users, so therefore some entries on the TLB won't be replaced by other entries, so they always sit there. And also, when the TLB is full, how to deal with the newly coming entry. So there are some replacement mechanisms that can be used to address this problem, such as first in, first out, or real risk first policy. But we are not going to talk about that here. So we just need to know, okay, there is a policy can be used for the replacement operation. In order to protect memory from malicious operations, the solution are shown here in this slide. So we have a protection bit with each frame to indicate that whether the frame is read-only or this frame allows read-write access. And also we have other bit to protect other properties such as whether the frame can be executed or not, etc. And also we can have a valid invalid bit to each entry in the page table to indicate whether the current entry can be accessed by this process or not. So when the bit indicates valid, it means the associated page is in the process logical address space and it is a legal page. Otherwise, the page is not in the process logical address space. The access request will be rejected. Surely, this is not the only way we can use to check the validation of the entry access. We can also use page table length register to do the checking as well, to see whether the logical address is within the range indicated by the page table length register. So whenever the violation result is caught, a trap will be triggered to the kernel. In paging allocation mechanism, there is a special type of a page called shared pages. The shared code is stored in the shared pages. For shared code, it is one copy of a read-only code shared among multiple processes. For this read-only code, so we call it reentrant code. For example, the shared code could be instructions for a text editor or compiler. Actually, this mechanism is quite similar to multiple threads sharing same process space. For this mechanism, it can save the memory space to allow more processes loaded onto the main memory. The figure on the right side of this slide shows us an example. We have three processes, P1, P2, and P3. For each process, it has 4 pages. And for the 3 former pages are instructions. They are the same in the 3 processes. The only difference is the 4th page in these 3 processes, which store the data. Actually, in this example, the 3 processes, they are sharing the same pages on the main memory. However, their data are stored on the different frames. For example, on your computer, you open 3 Word instances, one for writing assignment questions, one for answers, and the other one is for project report. For these 3 word processes, they share the same word instructions, but you are working on different data.